This is Radio TV Phono Nut, and what we have here today is the amplifier out of a Voice of Music stereophonic record player from the early 60s. I believe this came out of a tabletop model. They actually made two versions of it. There was a version with a manually operated turntable mechanism, and then there was a version with an automatic record changer, and I believe these models were very popular in schools, and they're decent units when they're working right. This one uses a 12AX7 driver tube and a couple of 50L6s output tubes, one for each channel. This set does not use a power transformer, however it does use a half-wave voltage doubler configuration, and that's a method they come up with for creating high B+ voltages for the tubes directly off of the AC power line without the need for a big expensive power transformer. This amplifier belongs to a friend, and they were having trouble with it as far as replacing the electrolytic capacitors. In fact, here are the capacitors they sent me. So I volunteered my services to help them straighten it out. They said during the course of working on it that this diode went up in smoke and blew in two, as you can see there. I don't know whether that happened because the diode was bad or because of some sort of wiring error or what. It really doesn't matter. You know, we'll get to the bottom of it one way or another. And before we dig into this, let me just give a word of warning here. I don't know what we're going to find. You know, like most everything else we work on, we don't know until we get into it. But if I see any negative comments regarding the workmanship or anything else regarding the previous repair attempt on this amplifier, those comments will be deleted. And the reason for that is because, you know, we're not doing this video to bash anyone. We're doing this video to try to get to the bottom of what's going on here, and as well as to try to pass on a little knowledge to those who may be watching the video. And also, any of us who have worked on electronics had to start somewhere. You know, we all started at the beginning not knowing very much. And I know I started whenever I was about 11 or 12 years old, and let me tell you, I knew very little at that time. And I made a lot of mistakes, and I'm just very fortunate that there were people in my life that were able to help me with those mistakes and show me where I went wrong without making fun of me. And now that I'm an adult, and have been an adult for quite some time, and have been doing this for a long time, you know, I try to do what I can to help others. Sometimes I'll run into someone who repairs vintage electronics, and they'll come across with a know-it-all attitude. In fact, if you don't do everything exactly like they think you should do it, then you're just an incompetent idiot. I remember in one of the Facebook groups a while back, well, it's probably been a year or two ago now, someone was running me and Shango 066 down in the dirt because, you know, we didn't have a shop full of fancy lab-grade test equipment. And, you know, in other words, we didn't do things exactly like he did it, so, you know, we were incompetent idiots in his mind. Well, on that note, let me just tell you that if you run into somebody, it doesn't matter whether it's electronics or what it is, who brags about how much they know and come across like they know everything, then you'd better get away from them, and get away from them quick, because they probably don't know as much as they let on. In fact, I've been doing this close to 30 years now, and I don't claim to know everything, not by a long shot. And in fact, each day I come out here I learn something new. And as long as I continue to work on this stuff, and as long as you continue to work on this stuff, you'll learn something new too. Your education will be never ending. And if you're someone starting out in the vintage electronics repair hobby, or even if you're someone who's been doing it for a long time, you will make mistakes. That's a guarantee. It's nothing to be ashamed of, and don't let anybody else make you feel bad because of it. Just as long as you learn from those mistakes, that's the key. I know I've blown up my share of stuff in my younger years, and even in later years I've wired things wrong because I wasn't paying attention to what I was doing or whatever, and suffered the consequences for it. So, with all that said, let's see how I'm going to go about this. I think the first thing I want to do is get rid of this big honking can capacitor, get it out of the way, and that'll give us some more room to work here. Okay, we have the old capacitor can out, and the values are, and these are all rated at 350 volts by the way, 80 microfarad, 40 microfarad, and 20 microfarad. Let's see what we have here in our what was sent to. We have an 82 microfarad 350 volt. That's perfectly acceptable for our 80 microfarad. In fact, you're going to have a hard time finding a modern production 80 microfarad capacitor. Here's a 47 microfarad 350 volt for the 40 microfarad. And here's a 22 microfarad, or is that 30? Yeah, I believe that's actually 33 microfarad 250 volt. The microfarad value would substitute for the 22, but I'd like that working voltage to be up a little higher. I'd like it to be at least 350, so we'll just use a capacitor from our inventory to replace that one. When replacing a capacitor, you never want to use a replacement with a lower working voltage rating than the original. For example, the 20 microfarad section of this old capacitor is rated for 350 volts, and I would want the replacement to be rated at least that much. If you go with a 400 or 450 volt, that would be perfectly fine, but we don't want to go lower. In this case, a 250 volt, that's 100 volts lower than what this one specifies, so that could present a problem. And another reminder when dealing with electrolytic caps is be aware that they are polarized, and on modern day capacitors the negative terminal is indicated by the stripe here with a negative symbol inside the stripe. And when replacing a multi-section can capacitor with individual capacitors like this, you tie all the negative terminals together just like they did here, so that part is correct. One thing I see that I don't believe is correct is this purple wire that's soldered to the lug on the terminal strip that's connected to the chassis. That purple wire was soldered to the ground lug on this capacitor, and since they have this capacitor in a cardboard tube, that means they didn't intend for the case of this capacitor to make contact with the chassis, so the way it was wired up here, that creates a hot chassis, and we don't want that. Okay, we're back, and I've done a little rearranging of the terminal strips. One of the problems I'm having is making this amp stand up where I want it. But one of the problems they were having was soldering the terminal strip to the chassis. That's the reason it was screwed in place. Well, in order to do that, the first thing you need to do is make sure both the chassis and the terminal strip are clean and shiny. And the best way to do that is take some fine sandpaper and sand the heck out of the chassis until it's nice and shiny, and do the same to the terminal strip, especially if it's an older terminal strip. It's oxidized and tarnished. If the chassis or the terminal strip are contaminated, then you're going to have a hard time getting solder to stick to it. Next, you need preferably a soldering gun. If you don't have one, or if the one you have happens to be indisposed at the moment, like mine is, you can use your standard pencil soldering station. It'll just take you longer to do it. Make sure your tip is clean, and then you'll want to hold the hot tip onto the chassis, and it may take 5 or 10 minutes to do that, so just be patient. And when everything gets hot enough, just flow some standard rosin core electronic solder and make sure it flows evenly and sticks to the chassis. If it balls up on the chassis or blobs up, then the chassis is not hot enough and the solder is not flowing correctly, therefore it won't stick correctly. Then you'll want to add a little bit of solder to the lug on the terminal strip to be soldered to the chassis, and then mate the terminal strip lug to the chassis where you've already flowed some solder, and then heat both the lug and the solder and the chassis up with your soldering gun. Again, this may take several minutes, and when everything flows together, carefully remove the soldering iron while holding the terminal strip in place with a pair of pliers, and carefully hold the terminal strip there until the solder cools. It'll take several seconds, and then it should be in place just like this is. This is not going anywhere. Now the next thing I need to do is figure out where some of these wires really go, and I think the best way for me to do that is to draw out a schematic on this piece of paper here. Sometimes it's easier for me just to draw it on paper, and then I can have a better idea of what I'm doing than just trying to just look at this without any kind of thought or anything like that. Okay, I've decided I'm just going to hold off on this until I can get the Sam's photo fact. Looking here, I see this big power resistor with something disconnected from it, and all this other stuff. Like I said, I think I'm just going to wait and obtain the Sam's photo fact, and then I'll know for sure. This capacitor here, one end of it was loose. I'm pretty sure that's an across the AC line capacitor, but I want to make sure. I found out this sand resistor is open. That's a fusible resistor, and it's supposed to open in case something shorts in the power supply. So I'm sure when this diode here shorted and blew up, that's probably when it took this resistor out. So yeah, we'll just table this until I can get the schematic for this, and then that way there won't be any guesswork. Okay, I found a Sam's photo fact schematic. Here's our two surge current limiting resistors wired in series. This is kind of strange how they've done this. They have a 10 ohm 10 watt in series with a 10 ohm 1 watt, and the 10 ohm 10 watt is the one that's open. There's our 100 microfarad voltage doubler capacitor, and there's our 0.1 microfarad capacitor. One end connects to the negative side of the doubler cap, the other end connects to circuit ground, and we'll upgrade that capacitor to an AC rated safety cap. And then here's our doubler diode. The anode connects to ground, cathode connects up here to the positive end of the doubler cap, as you can see, and then we have our rectifier diode connected to our 80 microfarad filter capacitor with a 500 ohm 10 watt resistor connected to that capacitor, and a 40 microfarad capacitor connected to the other end of the 500 ohm resistor, and then a 27K 1 watt connected to the 40, and then the other end connects to the 20. So this will help us out a great deal in straightening this amplifier out. Okay, I think I figured out why it went boom boom. See this white wire here that connects to where the first filter capacitor would go, and the output of the diode also goes there. You see it runs back around and is soldered to this lug here. Well, if we trace back, this white wire soldered to that lug goes all the way back around here to the input of the AC input of the surge resistor. I'll show you on the schematic. The wire was connected right here all the way back to here where the AC goes into the resistor here. That's the incoming 120 volts AC from your electrical socket. So I'm sure that's the reason things went boom boom. Now I believe if I'm looking at things correctly, and I'll double check before I do this, this wire should have actually been soldered to this resistor here. That's the 10 watt resistor in between the first two filter capacitors. And then as you can see, the red wire that solders to the other end of the resistor comes down here to this lug where filter capacitor number 2 goes. Okay, I used the desoldering braid and my soldering iron to clear out the solder to give me a nice through hole on this resistor. You just simply hold the desoldering braid over the connection to be desoldered, and then place your soldering iron tip on top of the desoldering braid, and in a few seconds you will see molten solder starting to wick up into the desoldering braid like what you see here. And this is the brand I use, Chemwick Rosin. 10-25L is the part number. I've tried the cheap stuff from Radio Shack back when we had a Radio Shack, and it didn't, well, let me rephrase that. It was cheap quality. It wasn't a cheap price. And it didn't work too well. The first few inches soaked up solder fine, and then after that I was just spinning my wheels. So, you know, if I'm going to buy 5 feet of braid, I want all 5 feet of it to soak up solder. And now we've bent this back into a J-hook, and we'll stick it through our desoldered terminal there and crimp it, and then we will solder it, and then that connection will be taken care of. And for hookup wire, I like to use stranded hookup wire because it's less likely to break than the solid conductor wire. And what I do before I solder the connection, I twist the wire to make sure there's no little strands sticking out, and then I tin the wire with my soldering iron and my solder. The way you do that, you just apply your hot soldering iron tip to the wire, and then touch a little bit of solder to the wire and let the solder flow through the wire, and the wire will be tinned. Now if it's an older wire that's corroded and oxidized, you'll need to sand the wire to get all the crud off of it, otherwise the solder won't stick to it. Now whenever I have multiple things to connect to a terminal on a terminal strip, I like to utilize all of the possible holes that I can use, and oftentimes what I'll do when connecting a piece of hookup wire to a terminal strip, I'll just run the bare wire through this bottom hole here, run it back through from this side, and bend the wire over and solder it. That way that'll be in place and out of the way, and then I can reserve this top terminal for our other things, in this case our filter capacitor and our diode. And speaking of diodes, these diodes in this set, these two right here, that one and this one, these are some early silicon diodes. This one here, as you can see, is blown to smithereens. This one still tests okay, but I'm gonna replace both of them with modern 1N4007 diodes just to be on the safe side. As old as these are and as primitive as they are, they could very well short on us and burn up stuff, and you know, we don't want that to happen. Once I'm done with this and return it back to the owner, I'd like it to last for a number of years if possible. And here's what we'll be using to replace our diodes. These are ECG 125s. They have a voltage rating of 1000 peak reverse voltage and a forward current rating of 2.5 amps. That'll be plenty enough for this application. 1N4007 is a common replacement that's cheap as dirt. You can order 100 of them for a few dollars from places like Mauser Electronics. These are just some that I happen to have got in with a bunch of stuff that somebody gave me, so I put them to use. Now, just like electrolytic capacitors, a diode can only be placed in the circuit only one way, And if you look at the new diode, the device on the left, you'll notice a gray band on one end. That is the cathode band. And when compared to the old diode that's blown apart, you'll notice the anode band of the new diode, which is the unmarked band. It translates into the yellow hump on the old diode. The cathode band will connect to the flat silver spot of the diode, and that's what that would look like here. So the cathode band translates on the old diode to the part of the diode that's flat and silver here, if you follow that. Now, this stuff here is called spaghetti tubing. I use it extensively to insulate the leads on parts if there's even the slightest chance that they might touch something and short out. You can get this stuff from Antique Electronics Supply, or you can use small diameter heat shrink tubing to accomplish the same purpose. You just cut it to the length you need and slide it over the component lead, and that way if the component happens to get moved around from vibration or whatever, there's no chance that the exposed lead will touch something else and create a short circuit. You noticed how I have it done here. We have our lead completely insulated. Our cathode band here, as you can tell, connects to the first capacitor, or where the first capacitor is going to be. We just simply J-hooked our diode lead, wrapped it around the terminal here, crimped it, heat our connection with the soldering iron. You heat the work, not the solder, and use just enough solder to get the job done. Okay, we have the filter capacitors mounted, as well as our two diodes, as well as the AC across the line capacitor, and we replaced this resistor here, as well as wherever it is, the carbon resistor that was in series with it. It was a little bit out of tolerance, and it's only going to just go up, so we went ahead and replaced it. However, we're still not out of the woods. I have our switch contacts jumped on the record changer plug, and I measured resistance across my power plug, and I should get a resistance of the tube string here, the filament string, and I'm not getting that, so let's see what we got here. Looking at the schematic, our hot side of the AC, once it's switched on, comes in through this 33 ohm resistor, goes back up here to this octal plug on the power supply chassis, and the main amp chassis plugs into that. That's pin 7, and pin 7, as you can see, connects to the tube heater string. So let's check that out. Okay, we now have a reading. Apparently our jumper clip wasn't making good contact there. So now we'll set the meter up to measure DC voltage. I'm going to plug this into our variable AC power supply, bring it up slowly, and make sure that at least the power supply is working properly. By bringing it up slowly, that helps prevent any more parts going up in smoke in case something else is wrong. Alright, we're connected to the main filter capacitor, the first one. Let's turn it on and see what happens. And I can tell things are off to a good start. We already have 37 volts DC on the first filter capacitor, and since this is a halfway voltage doubler type power supply, that's probably about what we should be seeing. I don't see any excessive current draw. We're now at about half line voltage, and as the tubes are warming up, you can see I can see the B+ voltage starting to drop. That's perfectly normal. As the tubes warm up and conduct, it places a load on the power supply and causes the voltage to drop. Now I'm increasing the AC input. Okay, everything on the power supply chassis is probably okay. Now we need to address the main amp chassis and most of the capacitors here are ceramic disc, but there are a few other types that need to be replaced, like these ceramic cased paper jobs and this plastic case paper job. I've seen those leak like crazy. Here's an electrolytic here, probably a cathode bypass capacitor. And here's a resistor here that's, as you can see, is busted half in two. So we'll need to find the other end of that and go ahead and replace it. And to make this a little easier to service, the two halves of this chassis come apart by removing two screws on this end and two screws on that end. Then we should be able to separate the two halves and make this easier to work on. And also 4 screws on this side. Oh, ain't that nice? Okay, it seems this doesn't separate as easy as I thought it did, so I'm going to have to just rely on what openings I've got here, and it is going to be a little tricky to do this. I've already found a little sloppiness from the factory. This resistor here that's soldered to the center post of the base control, it was just the lead just laying over on top of the control and soldered, and there really wasn't enough lead left for me to properly insert it through the hole and bend it over, so I had to add a little piece of wire to that lead and do it that way. This resistor here, basically the same way. It just came loose from the terminal here, so I had to add a little piece of wire to that so I could more securely connect it to the terminal here on the base control. Here's another example of factory sloppiness. Wanted to remove this resistor to make it easier to get this capacitor up and out of here. And as you can tell, they just had it laying over the terminal and block soldered. I must say I'm a little bit disappointed in VM for that. I would expect better from them. Okay, I'm getting there, and my workmanship is a little sloppy, but when something is packed up as this is, it's a little bit difficult to be unsloppy. Now I want to show you some more VM sloppiness. We have a 15K resistor running from the center of the base control, or the center of one section of the base control, back to this terminal strip. You have one leg of a disc capacitor and this orange wire connected there, and that's the only thing connected to that particular terminal. Now let's look at the other portion of the base control. 15K ohm resistor going to the terminal strip, disc capacitor, and a yellow lead there. Now you'll notice here we have a 15K ohm resistor. Nope, what is that? Yeah, it is a 15K ohm resistor. It looks kind of different under the camera, but anyway, my theory on what happened is this resistor was intended to go here, and it got busted off during the manufacturing process. Well, rather than take the busted out resistor out of the way, out of the circuit completely, they just simply left it there and tacked a good 15K resistor to where it needed to go here. So this actually doesn't appear that it went anywhere, and I can't find the other end of the busted resistor, so I think my theory is correct here. Well, looking at the schematic confirms my theory. All I've got to say is this particular unit must have either been a Monday job or a Friday job, because there's all kind of sloppiness here, and I don't mean sloppiness from a technician, I mean factory sloppiness. So we're just going to go ahead and get this out. Here's another oddity. This is our cathode bypass resistor for the audio output tubes. They're using the same resistor for both tubes. It's a 91 ohm resistor. Found that to be kind of an odd value for a cathode bypass resistor. Here's our bypass capacitor that we're about to replace. And then we have these two white Goodall capacitors that need to go, and then hopefully we can put some speakers on this thing and pass a signal through it. Okay, I just cut the cathode bypass capacitor out, and while it's out of the way, I think I'll go ahead and replace this Goodall capacitor. It looks like the chassis isolation capacitor. with one side connected directly to the chassis and the other side connected to circuit ground. We'll want to use an AC safety capacitor for that purpose, and it looks like this capacitor here might be something similar. We'll have to look into that. Okay, we have all of the capacitors replaced with the exception of the ceramic disc, and we don't mess with them unless there's a need to. Sort of went over all the resistors and they check pretty good, not spot on, but they're not bad enough out of tolerance that I'm going to bother to replace them. This thing will probably last another 50 years before they get bad enough out of tolerance to need to be worried about. Now, just for fun, I think I'm going to check the capacitors that came out of here just to see what kind of shape they're in, and I'm not going to waste time in this video showing you each individual component test. If I find something that looks questionable, I'll show it to you. Okay, I'm testing the 20 microfarad section of the electrolytic, and it seems to be a little bit on the leaky side. As you can see, the light finally went off, but it stayed on a long time before I shot that portion of the video. Well, amazingly enough, these 4 Goodall capacitors and these 2 pyramid capacitors check perfectly fine. They read within tolerance on the value and there's no leakage. These 3 electrolytics are still usable. They read a little high, but they could still be used. The only one that was a little bit on the iffy side was this can capacitor as far as the leakage goes, but you know, we could have probably left all this in there and it might have lasted for another 50-something years, or it might have gone out next week. So, you know, just to play it safe, we went ahead and replaced them, and I don't imagine the new capacitors will fail in a week, but who knows, these would have failed in a week either. But anyway, it's done now. I think they really wanted the capacitors replaced, so I always like to do what people want within reason. I'm not going to go rob a bank for you or anything like that, but as far as this electronic work, I try to be accommodating. Now, it's Thursday, and I think I've had about all I can stand for today, so tomorrow I'll stick the tubes back in it, connect a couple of speakers to it, and see if it'll pass an audio signal, and I feel like it probably will, unless something unforeseen is wrong with it, and if it is, we'll deal with it then. Alright, we're connected on the workbench to some speakers, ready to do the buzz test. That's the right channel. That's the left channel, and as you can hear, the left is considerably weaker than the right, so that means we still have a problem we need to deal with. I've already checked my voltages on the 7025 or 12AX7, and they look good. And if I touch pin 7, which is the control grid to the left channel that's weak, I just have to bring my finger close to it. Yeah, you can tell we have plenty of signal there. In fact, it's overdriving it majorly. So the trouble is somewhere between the left phono cartridge input, somewhere between there and the control grid of the 12AX7. So let's see if we can find out where it is. Well, actually the problem is nowhere. Or actually it was somewhere. It was the balance control turned all the way to one end. What did I say in a recent video about checking the obvious? That's the left and that's the right. Both of them appear to have the same degree of noise now. Okay, here we are connected to the tape recorder, and I got a little Al Hurt playing through the amplifier, and that's a tape that someone recorded off of a record album probably 40 years ago. I believe the name of it is Al Hurt Live at Carnegie Hall, if I'm not mistaken. And this thing sounds really nice. Now, it'll probably have more power when mated with the correct phono cartridge for this amplifier, because this tape recorder only puts out about a ½ volt output maybe, and the phono cartridge probably puts out a volt and a half. So, but still, this thing sounds really well for what it is, and we're connected to these realistic bookshelf speakers from the early 80s. They were pulled out of the trash pile at a thrift store. They're kind of banged up, but they serve my purpose. There's the right channel, and there's the left channel. Let's see what else we have here. Yeah, this tape deck was given to me by Jordan Tuck, also known as Speaker Freak 95. I'm sure many of you who watch my videos are familiar with him. He does a lot of the same type stuff that I do. But yeah, I think we're about ready to send this amp back to its owner, and they can reinstall it in the record player, and hopefully it'll be good to go for a number of years. Yeah, looks like that's all that's on that side, but
and I think it's fitting, since we're here, that before we go, we do something legitimate. And here's an old, what it is an old cornet solo played tonight on the trumpet. Consists of 7 parts. First part is a cadenza, an Italian musical. And the melody. This is.
You know, you young people watching this, this is how we found a song in the old days before CDs and digital files. We used fast forward and rewind until we got to the correct spot on the tape. And before the days of cassettes, there were 8-track tapes, and most 8-track decks didn't even have a fast forward button on them. All you had was a track change switch, and you selected the track that your song was on, and you let the track play out until your song came up. Okay, that ought to about do it for this. Thanks for watching, and more to come later. Okay, I guess we could briefly recap what was done before we end this. There were only a couple of wiring errors. The first was they had circuit ground, or B-, and chassis ground shorted together, which made the chassis ultra hot instead of kind of hot. With this 0.047 microfarad capacitor between circuit ground and chassis ground, that just makes it kind of hot. And also they had, where is it? They had a short between the output of the rectifier diode back here to the AC input, so that didn't make things too happy. And here I rearranged the mounting of the filter capacitors on terminal strips that are soldered to the chassis. I replaced both diodes with modern silicon devices. It should last a long time, hopefully. And I replaced the burned out surge current limiting resistor that likely burned up as a result of the wiring error. And this is our AC line to ground capacitor. I replaced that with a special AC rated safety capacitor. And on the main amplifier chassis, I cleaned all the controls and replaced any paper and electrolytic capacitors that were present, even though those tested fairly well and could have probably been left alone, but we all know how old capacitors can behave. They might go another 50 years, or they might go belly up next week. Okay, well that should really take care of it this time. I'll say goodbye for now, and hopefully we'll have another interesting electronic project on the bench very soon.